Hello once again, class, and welcome to another mock lecture. Today, we are going to be talking about power functions. Now, we're going to start off with the definition, which says that a function f given by f of x is equal to c times x to the b is a power function. C and b are both some real number constants, so you've got x being raised to a real number power, so not just whole numbers like with polynomials where you have like x squared or x to the third or x to the fourth. Now b can be any real number, like the square root of 7 or 1/2 or negative 2.9. If the b is a fraction, like 1 over n for some integer, where n is greater than or equal to 2, then we may call f of x a root function. So a root function is like a subcategory of a power function. And the reason that this is true is because if you have some rational, power like this, x to the 1 over n, you can rewrite that as the nth root of x. Or if you have some compound fraction where your numerator is not just 1, like 2/3 or something, then you can write it as the cubed root of x squared. So just as a very quick example, let's say you have like x to the 2/5. That's the same as the fifth root, so it's a root function of x squared. Now the domains of root functions is pretty interesting in the sense that it breaks up into one of two things depending on what this n is. If the n is an even number, then you're taking an even root. So like if it's x to the 1/4, that's the same as the fourth root of x. This is an even index. You cannot take the root of negative values. So the domain, you can only plug in things that are between 0, including 0, up to infinity, but like you would not be able to plug in like -2 into that thing. If n is odd though, then you can plug whatever you want into it. So, if you have x to the 1/5, that's the same as the fifth root of x. You can take fifth root of negative numbers. You can take the seventh root of negative numbers. For any odd root, you can take that particular root of negative values. That's fine. So you have to look at your function and decide what is the domain of this thing. Is it all real numbers or is it only all positive real numbers? Because that's the difference between these two domains, and it entirely depends on what the denominator of your fractional power is, right? B is the power of x. So for example, let's say that we let f of x be equal to 2x to the 2/3 plus 9, and I want to know what the domain is. Well, just look at the denominator of the fractional power. It's odd, and so therefore the domain is all real numbers, right? That's another way to say this thing here. If you have j of x equal to 1.6x to the 3/8 minus 7, well, here the denominator's even, so then it's only all positive real numbers. Now the rest of this video is going to be dedicated towards how to solve power equations. So let's look at some examples. All right, example number 1 says solve 2x to the 5/3 plus 1 is equal to 7. Just take note that the denominator is odd, and so we know the domain for this thing is going to be all real numbers. So we can get both positive and negative stuff. That's fine. Now, to solve these things, the first thing that you're going to want to do is you're going to isolate the x raised to whatever power that it is. Sometimes it's not just x that's being raised to a power, and we'll look at an example of that next. But for right now, we just need to isolate this thing, which is a two-step process. First, we're going to subtract 1, then we're going to divide by 2. So now we're done. This part is done. We've isolated x to the whatever. The second thing you're going to do now is you're going to need to get rid of that power. To do that, if you raise both sides to the reciprocal of whatever the power is, they'll cancel and you'll just get x to the first power. So the reciprocal in this case would be 1 over b. b is 5/3, so 1 over b is 1 over 5/3, which just flips the fraction because, again, it is just the reciprocal. It's 3/5. So if we raise this thing to the 3/5 power, notice that whatever you do to one side, you have to do to the other. But when I multiply these two things together, because that is how raising a power to a power works, you multiply the exponents, you get 15 over 15. That just simplifies to being x to the first, but we don't need to write that since we know they've just canceled, so we have x. You have to calculate 3 to the 3/5. You could plug it into your calculator to figure that out because it's not a nice number, but you get approximately 1.93. The explanation for how that works, by the way, is when you have x to the 5/3 and that's equal to 3, you can rewrite this using radical notation. So x to the 5/3 is the same as the cubed root of x to the 5th. And then so I had to cube both sides, which gives me x to the 5th is equal to 3 cubed, which is 27. Then you can take the fifth root of both sides or raise both sides to the 1/5, and you would again get back to 1.93. Let's look at this one, example number 2. You have something that's in parentheses. You have the quantity x plus 1 to the 2/3 plus 11 is equal to 15. So the thing to notice about this one is, yes, the domain is all real numbers again because we have an odd denominator, but in the process of solving this one, we will end up square rooting both sides. And anytime you end up square rooting something, you're going to end up with plus or minus stuff. Like both of them. You get plus or minus that particular result. So whenever you have x to the something, right, whatever this ends up being, if this is an even number up here, like 2 or 4 or 6 or whatever, that means that what you really have is you have x to that even number, I'll just stick with 2, divided by probably some odd number is going to be down here. Otherwise, this would have simplified, So maybe it's like the 7th root. Maybe there's a 7 that's down here. In the process of solving this thing, and you've got something over here, you'd raise both sides to the 7th power to end up with x squared is equal to some number. Actually, square rooting means you need to invoke the square root property, which is going to provide plus or minus the square root of whatever's underneath there. Okay, so something to keep in mind, something to look out for. When your numerator's even, you're going to get 2 answers, right, when you're done. Anyway, let's start off by isolating the x to the power here. Except in this case, the x to the power is this whole thing, right? This is like your x in this example. Only one step. Subtract 11, so we get 4. Now we can go ahead and raise both sides to the 1 over b, which is 3/2 in this case. Then these cancel. We end up with x plus 1 on the left. And then 4 to the 3/2 is something we don't need a calculator for. It's the same as the square root of 4 cubed. The square root of 4 being plus or minus 2, and then plus or minus 2 cubed being plus or minus 8. Now, you'll notice we're actually out of steps here, so we need to add another one. And that is, we need to solve now this simpler equation. Since we have x plus 1 equal to plus or minus 8, we should break that up into its 2 equations. X plus 1 is equal to negative 8, and x plus 1 is equal to positive 8. In both cases, you subtract 1 to solve, and you get negative 9 and 7. So again, anytime you have x to the fraction, m over n, right, and it's equal to some stuff, if m is an even number, solving it is going to produce a plus or minus on the other side of the equation, which is kind of fair, right? Like, so n controls whether the domain is all reals or just positive reals, but m gets to determine how many solutions there are, right? There's either 1 or 2. In this case, we got 2 because it was an even number in the numerator for the original equation, which means we had to square root at some point, which produced that plus or minus. Okay, example 3, it says solve 3x to the negative 1.37 plus 1 is equal to 19. I'm just throwing this one in to show you, and you shouldn't be scared of these types of powers, right? First, we're going to isolate the x to the b. It's, again, 2 steps, subtract 1, divide by 3. So here we go. Now, when you raise x to the negative 1.37 to its reciprocal, what would that look like? Well, it's just 1 over negative 1.37. Okay, so they cancel on the left here. And then if you type x to the negative 1.37 into Desmos or something, you end up with approximately 0.2704. Now, it's a little trickier to answer whether or not this is our only solution. 1.37 is a terminating decimal, which means it can be written as a fraction, and we'd have to figure out, well, is the numerator for that thing even or odd? Because that would determine whether there's 1 or 2 solutions. So just take my word for it on this one. This one only has just the one solution. And so notice there's no simpler equation to solve in this one as well, right? After we rose both sides to the 1 over b, that was just the answer. We're done. So we don't need this step for this one. All right, example number 4. Let's say we've got 2x to the 2/3 plus 5x to the 1/3 minus 3 is equal to 0. For which you might be saying, wait a minute, that's not a power function. And you're right. So let's go ahead and get this stuff out of here. Okay, to tackle this one, it almost looks like a polynomial, right? In fact, if I use some properties of exponents here to rewrite this thing as 2 times the quantity x to the 1/3, and then that's squared, plus 5 times the quantity x to the 1/3 to the first power minus 3 is equal to 0, if I could replace this with something, because it's the same value, they're both x to the 1/3, then actually this would be a polynomial. And that's what we're going to call U substitution. So U substitution is something that's oftentimes used in a math class to make something that looks kind of complicated into something that looks a little bit more basic. This is kind of your first introduction to it. But U substitution is used for basically every math class after this one, I would say. If you let x to the 1/3 be U, then now this is what our equation looks like. And we can factor that, or at the very most amount of work you'd have to do is use the quadratic formula, but you could still figure out that U is 1/2 or -3. A common mistake here is students will stop. They'll stop at this point and be like, I'm done, I found U, right? But we're not trying to find U, right? This isn't an existential sort of problem. We're trying to find x. Okay, so what we need to do is remember, wait a minute, U is x to the 1/3. So I'm going to now unsubstitute U and put back in what it was. U represented x to the 1/3, so that's 1/2, or x to the 1/3 is -3. To solve both of those, you raise both sides to the reciprocal of 1/3, which is 3, and so you get x is equal to 1/8 or -27, and we're done. Now, because you can just jump to here, you could kind of bypass the whole having to use U. Technically, this factors into 2x to the 1/3 minus 1 and 2x to the 1/3 plus 3. So you could technically bypass the whole U substitution thing, but that looks kind of complicated. This looks pretty simple. So I think stick with U substitution and then just remember, well, wait a minute, U represents x to the 1/3. You can do this when you have negative exponents as well. So this one I just showed the whole thing. The original equation is here. You have 15n to the minus 2 minus 19n to the minus 1 plus 6 is equal to 0. And what I did is I let U be n to the minus 1 so that I could rewrite it like this. Right? And again, I'm just taking advantage of exponent properties. Raising a power to a power is multiplying them. And -1 times 2 is indeed -2. -1 times 1 is -1. So I just noticed that these again were the same. That's why I decided to make U n to the minus 1. So I just replaced it with U, factored this into this, used my zero factor property, or really at this point the factor theorem, to get this. And then I had to remember, well, wait a minute, U represented n to the minus 1. So then I replaced it with n to the minus 1, and then to solve that, I had to raise both sides to the reciprocal of n to the minus 1, which is actually -1, because n to the minus 1 gives me just n to the first. And all you had to do when you raise something to a negative power here, these just flip, is all that happens. So 2/3 becomes 3/2, and 3/5 becomes 5/3. And then, so we're done. They can get a little bit more tricky. Like, for example, in this one, you have x to the 3/4 minus 2x to the 1/2 minus 4x to the 1/4. And you might say, well, what am I supposed to make U in this example? None of the denominators are the same. Or I guess, they're not all the same. The middle one's not the same. Well, 1/2 can just be unreduced into being 2/4. And now you do have the same denominator for all of your exponents. And in fact, the numerator is 3, then 2, then 1. So what you could do to make it something cubed minus 2 something squared minus 4 times something plus 8 is you could just break up those fractions. Every single piece is going to be x to the 1/4. So you should make x to the 1/4 be U, right? And then you're kind of off to the races from here, right? I'm not going to finish this one, but you can. What I recommend doing is grouping. Use the grouping methodology, and then that should work out nicely for you. Or you could just graph and then look at where the x-intercepts are. Keep in mind that those would be U, so whatever those x-intercepts are, you have to set x to the 1/4 equal to that thing, and then raise everything to the 4th power to figure out what x is equal to. Anyway, I think that's long enough. I just wanted to kind of introduce power functions, show you guys how to solve polynomial-like sort of things, that they aren't power functions, but you end up solving a mini power function at the end of it when you unsubstitute U. So hopefully that helps. Hopefully you learned something. If you have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.